All right. Is that it?
Looks like it's the bottom.
Looks like it's the bottom. I feel like I'm...
Or something being orthogonal, that means that you've got your group of angles are all at right angles to each other?
Yes, but I thought it was here, but it's going to be the next section. I'll define that explicitly.
Okay.
Right now, we know the word perpendicular, and everyone's comfortable with the word perpendicular?
Yeah.
Okay. So let's get on. We're going to move on to the next note. As a reminder, in terms of our schedule, as far as our schedule is concerned, today we are trying to get through as much as we can of the dot product. So today we're supposed to be doing vectors and dot product. I'm going to try and get through some dot product now. It'll carry into next class, I'm sure, because we only have 40-something minutes. 30, yeah, sorry, we leave 33 minutes. All right, so I said there are three types of multiplication, right, when it comes to vectors? So this is interesting, I think, all right? Is there a question? No. Okay, I thought you were raising. All right, so look, scalar multiplication, you're taking a vector and a scalar, vector and a number. You're multiplying them together, and what comes out? Number times vector, you get a vector, right? Number and vector, you get a vector. How do you put two vectors together with multiplication? Not addition and subtraction, multiplication. How do you multiply two vectors, right? Seems like a natural question. How are we going to define that? Well, there are two types of multiplications where you put two vectors together. The first type of multiplication is called the dot product. The second is called the cross product. This section is about the dot product. So the dot product, it's also called the scalar product. It's also called the inner product. That word scalar, wait a minute, scalar multiplication, didn't we just talk about scalar multiplication? Yeah. So don't confuse the two. Scalar multiplication of a vector is a number times a vector. Here, to distinguish between the two, you'd say the scalar product, and then you'd be talking about the dot product. Most of you are going to see dot product. Math majors, eventually this is going to turn into an inner product, and there's all types of different types of inner products. All right, so this is, the dot product is one particular kind. All right, so here it is. Given two vectors in two-dimensional space, we'll start in two-dimensional space. We define a new type of product between them as follows. So we have two vectors, v and u, and here's the definition. It's u with a pretty big bolded dot. In most textbooks, it'll be distinguishable from the dot we usually use for multiplication. It's like bold. U dot v is simply, check out what it is. This component times that component. So you multiply the x components, and then you add the y components multiplied together. And then your answer is going to be a what? What comes out? Is it a vector? Careful. It's a number, right? It's a scalar. It's a number. This is strange. The dot product takes two vectors and gives you a number. Right? That's what I'm saying. I'm saying you take two vectors, you dot them together, and you're going to get a number. That's the definition of what the dot product is. Yes? Yeah, so the next natural question would be, well, what the hell does that number mean, right? Like, does it have any sort of like significance, right? It will. Hold on. Let's talk about dot product in three-dimensional space. So I just say here, dot product is the sum of the products of the components. It's vital to notice that dot product yields a number. Okay, the answer is not a new vector, and the bolded dot, okay? Look, this has not happened to us very much ever in our mathematical lives, right? Even when we had functions back in algebra, if we multiply two functions, our answer would be a function, right? You multiply two numbers, 4 times 7. Your answer is a number. Here we're taking two vectors, and, taking two cats and getting a dog. Right? It's like, this is weird. Okay, so we'll have to make sense out of this in a minute. All right, so how do we do it in R3? Three-component vector. All you do, multiply the first components together, then the second components together, then the third components together. Add up all that, you're going to get a number. This shouldn't take us but 30 seconds. Here's V, here's U. Dot the two.
All right.
Does the order matter, do you think?
No.
Does the order matter? Why not? Okay. It's multiplication, isn't it? Like we're multiplying two numbers together. Has that ever mattered, what order we do that in? No, so it doesn't matter. And I'm going to give you some properties in a second. That U dot V is the same as V dot U. You can switch the order. But to follow the note from before, I'm just going to write this. U dotted with V would be, okay, I'd start with the first component of U, -3, and I multiply it times 2. So what I'm doing there is multiplying those two together, right? Plus, notice that I am not putting an angled bracket, right? I'm not doing a vector here. I'm just doing a number. And then I'm going to take the 4 times -3. And then finally add to that the 7 times 5. Up 7 times 5. All right, this is going to be -6 minus 12 plus 35.
Which is 17.
Is it? 17? Yeah. My brain, when it comes to arithmetic, my brain just shuts down. I don't feel like doing it. Everyone agree with 17? Okay, good. All right, so it's a number, right? What does that number mean?
I have no idea.
Yeah, no idea, right? All right, so before we figure out what it is, okay, our answer is 17. That's it. Before we actually discuss what it is, let me give you the properties of the dot product. The first one is really a cool property. If you dot a vector with itself, right? Can I erase this? What happens if you dot a vector with itself? It's the same as taking the magnitude squared. Why? Why? Let me see if I can. Let's say I have a vector U. Okay, let's say it's a 3-dimensional vector. Okay, there's a vector U. It lives in 3-dimensional space, right? Yes? Okay, now, if I ask you what the magnitude of this is, you're going to take the square root, and then what you're going to do is you're going to take that square plus that square plus that squared, right? Yeah. So you're going to have U1, you're going to square it, plus U2, you're going to square it, plus U3, and then you're going to square it, right? This says that if you dot a vector with itself, right, imagine dotting this vector with itself. You would do this times itself, plus this times itself, plus this times itself, right? Mm-hmm. Which is the same as this thing, but without the square root. Yeah. So you would have to square this magnitude to get rid of the square root, which is what this is saying. You follow? Yeah? It's just a nice property of it, that's all. Do I need to go through that in more detail? Okay, this says that the dot product is commutative, so you can flip the order. That doesn't matter. Yeah. And that's just because multiplication is commutative. All right, the next property is that you can distribute over addition. So this is really weird. If you take a vector and dot it with the sum of two vectors, that you're allowed to distribute the dot product through, and it'll become U dot V plus U dot W. We'd have to prove that more. We're going to take it as a property. We're just going to take it on faith at this point. Property 4 says that if you have a scalar times U and you dot that with V, that you can move the scalar around anywhere you want. You can bring the scalar out, dot them first, or you can even move that scalar onto the V and then dot that answer. The scalar just can go wherever, you can place it wherever you want.
Yeah, I mean, because it's multiplication.
It's multiplication, so you just slide it around. Say again?
There's a specific word that C is triggered where you can distribute it wherever you please.
Well, it's not distribute, it's commuting. It's commutative. All right, and then of course the 0 vector times any vector should be the number 0. Right, think about what the 0 vector looks like, right? It's like 0, 0, 0. Yeah. And if you dot that with any vector, you're going to zero out everything. So you get the number 0. I think I'm going to skip example 2 because all you have to do on your own is, find V plus W. So add V and W together, add them up, get a new vector, dot them together, dot it together with u, and then multiply the whole thing or scale it by 3. I'm going to leave that. I want to get on to the theorem. What does this number represent? Right? So here it is. This is a huge, huge theorem. Very important theorem in calculus. If theta is the angle between two vectors u and v. So let's back up. Here's two vectors in three-dimensional space. Here they are, right? Let's say that one's pointed that way, that one's pointed that way. So that's your tip, this is your tip. Okay? I can always move them, as long as I don't change the direction, scale them, I can slide them around until I get them tail to tail. Right? I can always do that. So now they're tail to tail. Do you all see that there's an angle between these two vectors? We're going to call that angle theta. All right? The theorem says that if theta is the angle between two vectors, u and v, then the following is true. The dot product, which is a number, right, is just the length of u, it's the length of this vector, times the length of this vector, times cosine of the angle between the two vectors. That's what the dot product gives you. So the dot product is a product of the lengths of the vectors times cosine of the angle between them. Can you hold on for a second? I want to get to the whole thing. Hold your question though. All right? So that's the theorem. Take it for now. And let's see what the results of this mean. So what if I tell you this? Here's the two vectors. I slide them tail to tail like this. What if I tell you that the angle between them is acute? That means between 0 and 90 degrees. Okay, think of an acute angle. And I want you to go back to your unit circle when you're studying. Remember on the unit circle that if you have an angle here, theta, this point has an x and y coordinate, right? The x coordinate is what trig function? Cosine of theta. And the y coordinate is sine of theta, right? So we're talking about cosine theta here, right? In this theorem. So let's ignore this for right now. If your angle is acute, what is cosine of theta going to be? Positive or negative? It's positive, isn't it?
Yeah.
It's a positive number. With me?
Yep.
So if your angle here is acute between 0 and 90 degrees, that means you're in the first quadrant. That means cosine, your x-coordinate must be positive. So that means your dot product would have to be what? Well, the magnitude of a vector is positive, isn't it?
Yeah.
And so both of these are positive numbers. So you're taking two positive numbers. And if the angle is acute, then that's a positive number, which means that the product of all of those should be positive. Which means I can tell you that if your dot product is positive, there's an acute angle between the two, right? What if your angle is obtuse? Now you're over here, aren't you? What's cosine over there? Negative. And therefore, that's a negative number. These are always positive, right? So if your dot product is negative, I can tell you there's an obtuse angle, right? Y'all following? Dot product positive, dot product negative. Now the big one. Perpendicular. What's the dot product? 0. Right? Because what's cosine at 90 degrees? 0. And so if we're straight up like this, right there like that, then it doesn't matter how long u is, doesn't matter how long v is, right? That's 0. And so that's actually a quick, easy way to check if two vectors are perpendicular or not. All you have to do is take their dot product. And if their dot product is 0, they're perpendicular. It's a simple check. What if the angle is 0? What if they are parallel? Like this, like pointing in the same direction like this.
Your cosine would be 1.
It would be 1, wouldn't it?
Yeah.
Which means that the dot product is actually just giving you the lengths multiplied together. So if this one is 2 units long, and this one is, this one's 2 and this one's 3, right? Then your dot product would be 6. if they were pointed in the same direction? What if they were pointed in opposite directions like that? That one's going that one, that one's going this way.
You have a negative one?
You get negative, right? The only thing that would change is that would be cosine of theta would be -1, so you get the lengths multiplied, but then negative. Say again?
When you only know that's an obtuse angle that's pointed in opposite ways.
Wouldn't you only know it's obtuse if they pointed in opposite?
Yeah, if it was a negative cosine.
I'm not sure I'm following the question. Anyone following the question? I'm not sure I understand it. I'm saying, let me restate. If your dot product is negative, then you know the angle's obtuse, right?
But is there a way to know that it's parallel in opposite directions?
If your answer is exactly the two lengths, but negative. That's how you would tell. It's not an easy check. It's not like perpendicular, right? Now it turns out that we're going to learn the cross product. The cross product, there's an easy check to see if they're parallel. So for dot product, it's a quick way to check for perpendicular. Cross product is a quick way to check for parallel. We're just not there yet. Okay. No, your question, did you have one or no?
Really quickly, so
Yeah.
Sine, conventionally, we use sine as opposed to under or below a reference point, so like on the bottom octaves.
We use sine.
Yeah, so like, for example, we have a vector that's on this side.
No. The theorem is always cosine.
So we use negative pi, like the reference point of what that angle is. From the pie chart, we use that negative or like that. Because we'll have like our theta would be an actual value. And we can't just put cosine of the full value that we have based on like where our direction is going. Does that make sense or? Okay, cool.
I'm trying to understand it, but
No, I can talk to you about it.
Yeah. The angle is the angle between the two vectors. It's not one vector like pointed out here and then theta has anything to do with this. It's two vectors, bring them tail to tail, the angle between them, smallest angle between them. So we have this angle between them, then we have the angle that goes all the way around. We're talking about the smallest angle between them, that's theta. So it can only be between 0 and 180 or pi. That's it. Because if I go past it like this, then the angle we're talking about now is this one right here, not that one anymore. Question?
So how would you go first that angle? So you did it like when you did it, the ruler going that way. Would you get all the way lower? How would you measure that angle? What would you call that?
That's still theta.
Well, because they're vectors.
Theta's always going to, yep, because,
You can move them around, so it doesn't matter, right? So,
yeah, these vectors, so if it was like this, right, then imagine pull these apart. Imagine they're like that. You'd pull them together, right, like that. And then we're talking about that angle, right? Like this angle right here. Theta is always going to be the smallest angle between the two. Not the bigger one, the smaller one. You sure?
No, it's just, so say if you had it like this, you can measure that as like, I don't know, 135 degrees.
Okay.
Now you have it the other way.
Yes.
Who wants to measure that?
The theorem says that the angle has to be the smallest angle between them. It's implied that it's the smaller of the two. There's this angle, and then there's this angle, right? There's two angles between these two vectors. Theta is always this one, the smaller of the two.
I think he's asking like if it's in one of the bottom two quadrants, how would you what number?
We don't have quadrants. We don't have quadrants because we're anywhere. You know what I mean? Like I'm anywhere. I'm in three-dimensional space. Like I don't have. I think yeah.
Or just on, like, in reference to the circle, which is what we were previously looking at.
Yeah, in the reference to the unit circle, your angle between the two vectors can only be between here and here. That's all you can be, between 0 and pi.
Because that's the balance.
Because two vectors tail to tail, that's the biggest angle you can get is 180. If you go past it, then you're talking about the other side, which is smaller than 180. No?
Question.
Yeah.
So this, I feel like I kind of already know the answer here. Oh, look, I think we might be bumping up on the answer here.
All right, so let me keep going.
Back off.
Yeah. All right, so this is me summarizing the whole thing about the angle is less than pi over 2 if we're in the first quadrant, then, or, you know, like off the unit circle, if we're in that first quadrant, then we're going to get a positive number. negative, but this is the big one right here. Right? If the angle between them is pi over 2 or 90 degrees, then they're perpendicular vectors. And perpendicular, another word for perpendicular is orthogonal. To say two vectors are perpendicular is the same as saying they are orthogonal to one another. It's just a fancier word for perpendicular, all right?
There's like no other purpose for it?
It's just a more technical term. It's just a more technical term. So when I was talking about orthonormal basis, I said IJK or orthonormal basis, right? Ortho, perpendicular, normal, unit length, basis, they span the space. So it's just another word. So two vectors are orthogonal if and only if their dot product is 0. Since I do have some math majors in here, have y'all talked at all about if and only if? What this statement means? Have you talked about this a little bit? Touched on it. So this is actually a very, very strong statement. Exactly. So it's like this. If I write this, this is my classic example. If I'm from Texas, but let me say that. If I'm standing in Texas, then I'm standing in the United States. Do you agree? Right now, at least. Yes? Can I switch that around? If I'm standing in the United States, then am I in Texas? Could I be? Yes. But is it absolutely a condition? It's not true all the time. So this statement is true all the time. This statement is true sometimes. So if they were true, either way I wrote them, if it was true both ways, then what I would write is this. Texas, if and only if, with two F's there, US. That's what I would write if it worked in both directions. This would mean if I'm in Texas, I'm in US. If I'm in the US, I'm in Texas. That's the way I'd write it. So if and only if means this statement can be read both ways. U and V are perpendicular means that the dot product is 0. And you can read it the other way. The dot product is 0 means that they're perpendicular. You're allowed to read it both ways. That's what the if and only if statement. Do not assume that you can read statements both ways all the time, especially in theorems. If it says if this, then that, that's the only direction you can read it. If it says if and only if, then you're allowed to read it both ways. All right, keep going.
So I have a quick question to do with things being perpendicular.
Yes.
In 3D space specifically.
Yes.
So in 3D space, if you have your, lines are perpendicular to each other,
Mm-hmm.
Things being perpendicular is only really dependent on 2 dimensions, isn't it?
Mm-hmm.
Because this is still perpendicular, isn't it?
Mm-hmm.
It's not perpendicular on, this axis, but it is on this one.
These vectors in 3-dimensional space are perpendicular, right? Orthogonal?
Yes.
These are? So are these.
Yeah.
That's what you're saying?
Yes.
Yes.
I just wanted to clarify that.
Right? I can rotate this around. These are still orthogonal. Same with this. Still orthogonal, right? So the idea, you could actually, from here on out, you could define perpendicular as being the dot product is 0. You could totally go away from the whole geometric description. And you could just say, as long as the dot product is 0, you're talking about orthogonal.
That's fine.
But that's a good point to bring up, because I'm kind of assuming that you see that. So the fact that you bring it up is
I
good.
was thinking I was seeing it, but I wanted to clarify that I was seeing it correctly.
So this is just a visual thing you can play with. What it does, the calculator computes the dot product for you. You just take these 2 vectors and kind of drag them around. See how it's an obtuse angle? Mm-hmm. And now look what happens if I go to the other side. See how it flips it over? Now we're talking about the angle here. See, it's still negative, negative dot product, negative, negative, until I get straight up and down, should get 0. Who cares? It's 0 up top, right? And then if I go acute angle, positive dot product. What am I doing here? Oh my gosh, we still have so much to do. I think I'm just going to talk through these. All right, so if I give you the magnitude of V and the magnitude of U, and I give you the angle between them, can you find the dot product? Yeah, because you can just go to this formula, right? Right there. I gave you the magnitude of u, gave you the magnitude of v, I gave you the angle, didn't I? So you just get your calculator out, make sure you're in degree mode if I give it to you in degrees, make sure you're in radian mode if I give it to you the angle in radians, and you just plug in the numbers multiplied times cosine on your calculator. Now in this particular example, you'd be in degree mode because I gave 31 degrees, right? Are these two vectors orthogonal? Yes or no? How? How do you know?
I multiplied the first two.
First two together gives you 6. These two together, negative 12. Add those up. What do you get? 0. These are orthogonal vectors.
Yeah.
See how quick and easy that is? You do the dot product. This times this, 6 times 2 is 12, plus 4 times negative 3 is negative 12. That adds up to be the number 0. So if you graph those two, they will be orthogonal to one another. All right, how about this one? This is similar to a problem on your take-home, except your take-home one is much harder. I think it's a dot product. I can't remember now. Look at this. It's on the top of the take-home. I don't know. February 8th, I think. Okay, so look. Here's the vector u and v. Find A such that these are orthogonal vectors.
Set them both equal to 0. And then
Set what equal to 0?
start doing the dot product. Set it all equal to 0.
Yes, do the dot product, set it to 0, right? That's what you need. So do your dot product. This times this is 2a plus this times this, negative 6a. Maybe I'll change that. Minus 6a. And then plus this, that's minus 12a. You need that to be 0, right? That's what you need to solve for a. Now that's an easy equation to solve for a, really easy because it's just a little linear equation. But I believe the one on your take-home is much more complicated. Much more complicated. All right, I'm going to keep going. By the way, the answer to that, the only solution to that is 0. A is 0 is the only answer.
Yeah.
So,
I mean, it would also just be the easiest one, no matter what.
what would?
Even if there are other answers, 0 is an immediate, obvious, and very simple one.
For that one, for that
this-
particular
yeah,
example.
For this one in particular.
Yeah. All right, so a little bit more about the theorem, that real important theorem that I didn't prove, I just gave to you. And that is, if you have two vectors, right, I give you two vectors, you can find the angle between them. All right, so we know that if we're given a vector, we can find out how long it is, right? But if I give you two vectors, can we find the angle between those two vectors? Well, here's the theorem. Now, all this is, go back up to this right here. I'm not going to do this by hand. I'm just going to talk you through it. If I asked you to solve for theta right now, okay, if I asked you to solve for theta, what you would do is first divide both sides by this, right? Get rid of those numbers, bring it over here underneath. And then to get theta out of the cosine, you would take inverse cosine on both sides. And that's exactly what this is saying. Is that to find theta, you take inverse cosine of the dot product divided by the magnitudes of the vectors. Now, 5 minutes. Let's see if I can do at least one of these. I'm going to talk you through this. Let's see if we can get this in 4 minutes, 5 minutes. This, to me, is like the awesomeness of the dot product theorem, all right? I'm giving you the corner points of a triangle in three-dimensional space.
Oh, that's a piece of
Okay? So there's a point somewhere, three-dimensional space, another point, and another point. Those 3 points create a triangle, right? I want to know if that's a right triangle. Okay, so let's talk through this, because I will not have time to do it. These are 3 points, right? They're sitting in three-dimensional space, not on a flat sheet of paper, right? They're out here. Let's just label them. It's totally arbitrary. Why do I not care how I label these? Why do I just kind of put them wherever? Why am I not concerned about their position on this page? It's R3, right? So it all depends on where you're standing, right? What this triangle is going to look like to you.
Yeah.
It might look like this. If you're standing on the other side, it might be something else. So it's completely arbitrary. I don't know if this is the right triangle. I have no idea, right? No idea. Anyone have an idea of how we could attack it, though? Be careful. Think about it before you answer.
Dot product until you find a zero answer.
Okay, you're going to use a dot product and look to see if you can find a zero, right? Dot product of what, though?
Use the two
Each
smaller.
possible combination.
Hold on. Here? What?
Find out the two smaller ones.
Two smaller what?
The two smaller vectors.
Vectors.
Two
Where?
smaller magnitudes of the. Like if that's like U, V, W, right? And
Okay, hold
it's the
on.
largest, that's
What's
the
U? What's V? I want to label U and V up here.
So U would be the bottom one.
Bottom what?
The bottom vector.
Okay,
Right.
so it's a vector. So it has a length and it has a direction,
Right.
and it has a mag. So how do you want to draw it?
Just down on the bottom. I mean, like the bottom line.
Bottom line segment or a vector?
Vector.
Okay, so how do you want me to draw it? I'm challenging this because this is the thing you have to put together. I've given you 3 points, right? I've not given you any vectors. You want me to do a dot product and get 0? You want me to dot vectors, don't you?
Yes.
I don't have any vectors, right? So continue. I'm going to get. You're asking me. You're telling me to do something with this, right?
Yeah.
But what do you need here? You said you wanted me to draw a vector, right?
Yeah.
Okay, so vectors. Like you want me to draw this?
Yeah.
Okay, like an arrow, like this, right? Okay. This is a vector, right, everyone? All right. What is that vector? How do you get that vector? It's got angled brackets, right? How do you get that? You have to do the subtraction, right? You're going from one point to another, aren't you? You're like going from A to B. How do you do that? We started class with that, didn't we?
Subtract the beginning point.
Exactly. So do you feel like you could get that vector?
Yes.
Okay. Now, you want me to take that vector and dot it with what other vector?
The one going from 204 to 625.
Okay. So you want me to do the different vector that goes from here to here?
Doesn't matter which one.
Yes.
Yes.
You want to go here to here? Call that, let's see, this one we'll call U.
Call it B.
Let's call this one V. Is that okay? Right?
Right.
Now, you know how to get that vector? You're going from this point to that point? And then once you have those two vectors, what are you going to do with them?
Trying to find it closer.
Find a zero.
Dot them, right?
Yeah.
Dot the two together. And what if you get 0?
Then you have a right angle.
Then you have a right angle. If you have a right angle, you have a right triangle, don't you? What if you get something other than 0?
Then we find our third side and check dot product.
Then you have to go to the other one, create a vector, and check that as well.
Because we check our
You only checked one angle.
Yeah, and we have to check our third side with U as well.
Now, if it were me doing this, okay, if it were me, what I would have done is on this one, I would have this is just me, I would have done the vector going this direction. Now, all that changes is the signs of this vector, but I like to think about the dot product this way. I'm trying to find the angle between those two vectors, tail to tail. Now, it turns out it wouldn't have mattered